Welcome back. We continue with the second leg of density-based clustering, now HDBSCAN, which stands for hierarchical DB-scan. And as we did for DB-scan, we'll start with some jargon, with some concepts, then I'll step through the algorithm and close with an illustration. So DB-scan was great, it was easy, but it was very sensitive, and if you did the lab, you will have some sense of that, to the selection of the critical distance, the epsilon distance. And also we have this strange concept of border points, and to some extent a degree of arbitrariness as to which cluster the border points are assigned to. In the algorithm, they are assigned to the first cluster that is encountered, which may not be optimal. The clusters obtained by DB-scan are referred to as flat clusters, and shortly it will become clear why this distinction is important. In essence, what it boils down to is that the same epsilon distance, epsilon threshold is used for all the points. So the bandwidth, so to speak, is fixed and will move to some more flexible notion of a bandwidth with the concept of a mutual reachability distance. And the idea here is that every point has associated with it what is called a core distance. And the core distance is, if you can think of the nearest neighbor terminology, an adaptive bandwidth. So the core distance, rather than being fixed, as it was the case in DB-scan, now becomes a function of the minimum points criterion. The minimum points criterion is turned into a k nearest neighbor criterion, and the core distance is a distance necessary to reach the kth neighbor. So it's a distance, how far you have to go to reach that neighbor. And think about this for a second. If a point pattern is very dense, you don't have to go very far to reach the nearest neighbor. On the other hand, if the point pattern is not dense and the points are very spread out, then for the same k, you may have to go quite a bit out. And so to penalize, in a sense, low density regions in the algorithm, the actual distance between the points is replaced by a new distance concept, which is this mutual reachability distance. And the mutual reachability distance between 2 points is the maximum of the core distance, so the distance to the kth nearest neighbor of each of these points, and their actual physical distance. So what does this mean in practice? Well, if the points are close together, then their nearest neighbor distance will not be much different from their actual distance. On the other hand, if the points are far apart, then to reach k neighbors, you may have to go much further than in a dense point pattern. And that's illustrated here in the top graph. So for a dense point pattern, to get your k minimum, you don't have to go very far, whereas for a not low density pattern, you do. And so see what this means in terms of affecting the distances between the points relative to their core distances. Here, it really pushes them much further apart than it does here. And you can see this in this kind of visual representation. Here is a high density region of the points, which doesn't change that much in terms of the relative positioning, whereas these points in a low density region get pushed out, so to speak. And so the essence is that the actual distances are replaced by this new concept, a mutual reachability distance, and that then is used to construct a minimum spanning tree. We haven't really talked about this yet, and I won't go into too much detail at this point, We'll revisit the minimum spanning tree later on when we deal with the various cluster techniques. But it is a simplified graph representation of points. So we already saw the connectedness graph in our discussion of spatial weights in the Intro Spatial Data Science class. So the connectedness graph shows for each point what other points are within a critical distance. And so a point can be connected to more than other points. And in a graph representation, that is the graph representation, each point is a node, and each connection is a link or an edge in the graph. And now what we're doing with this representation of our points, we replace the actual distance by this minimum reachability distance. So we keep the points as they are, but we move them out as needed and represent the length of the edge that connects them. That corresponds to the minimum reachability distance. And then we take this graph, which is, has many points connected to many other points, and reduce it to a minimum spanning tree. And a minimum spanning tree is a graph that where one can pass through each point just once. And it connects all the points with a path that goes through each point just once. So it's a great simplification of the complexity of the original graph. There's a number of different algorithms to accomplish this. The most common one is called Prim's algorithm. We'll talk about that more later. The essence is that we take our points, we replace the original distance by the minimum reachability distance, and then we represent the spatial structure by a graph, and then we turn this graph into a minimum spanning tree. And now we can make cuts in this minimum spanning tree. For example, remember our epsilon distance threshold that we had before in DBSCAN, we can look at which edges, these are distances, which edges meet or do not meet this critical distance threshold. And if they don't meet them, we cut them. And we can cut them, and each of these cuts creates a subset of points. Like say we cut here, we have a subset of points that we then call a cluster. So the process, the logic is actually pretty straightforward. You have a set of points, they are given distances apart. You introduce this new concept of distance, which is the core distance, and then use the core distance to push the points around so that the new distances that separate them are these minimum reachability distances. Then we take the connectedness graph with these minimum reachability distances and turn them into a minimum spanning tree. And then the minimum spanning tree, we can cut the edges that do not meet a given distance criterion. Now, as it turns out, and we'll discuss this again in more detail when we talk about clustering, the structure represented by a minimum spanning tree and the cuts in a minimum spanning tree is equivalent to a single linkage hierarchical clustering dendrogram. So a dendrogram is a representation of how the elements are grouped together as we look at the distance that separates them. So what this means for us, and this algorithm is called DBSCAN star, is we take the minimum spanning tree based on this new mutual reachability distance, and then we have a so-called flat cluster, as I mentioned, which is a cut at a specific core distance, and the core distance is the inverse of the density. So the smaller the distance, the higher the density, the larger the distance, the smaller the density. And so this, as I mentioned, and we'll get into that in more specific later, is equivalent to single linkage clustering. And so what we have here is a dendrogram. And the way this is constructed is we take the 2 points that are closest together and connect them. And then we take the next ones that are the closest together and connect them. And so we get this tree structure, and we'll see this in more detail when we discuss hierarchical clustering. This tree structure shows how we go from each point being its own cluster to all the points forming one single cluster. And applying the cuts to the minimum spanning tree is equivalent to applying a cut to the dendrogram that corresponds to the grouping of the points using their mutual reachability distance. And so this will then, these cuts, each of these cuts yield a number of observations that are together and that are form a given cluster. So a couple of new concepts. We have the concept of a core distance, which is the inverse of the density. We use this core distance to create a new concept of mutual reachability distance. That forms the basis of a graph representation of our points with this mutual reachability distance corresponding to the length of the edges. Then we turn that graph into a minimum spanning tree and apply a cut for a given core distance, or in other words, for a given density. They're the inverse of each other. So the smaller the distance, the higher the density, and vice versa. And this is equivalent to constructing a single linkage hierarchical cluster based on a mutual reachability distance and performing a cut in the resulting dendrogram. Now, what is undesirable about this is this notion of a flat cluster. And the contribution of the novelty, if you wish, of the hierarchical DB-scan is that it moves away from this flat cluster and, in fact, applies a different notion of core distance or density cutoff. You know, the two are the inverse of each other, so it doesn't really matter which one you use, but they come down to the same thing. So the essence of the hierarchical DB-scan is that a couple of new concepts are introduced. And a very important concept is excess of mass. And the excess of mass, in a sense, is the amount of density left in a distribution after you apply a level set cut to it. So if you can think of it as, in using our island analogy, so we have the sea level and the islands stick out above the ocean. What is the area or the volume of the island that is above the water? And as the water goes up, that area will become smaller. As the water goes down, that area will become larger. So we're interested in finding out what is the area under the density curve after a split is formed. Remember our original graph in the previous lecture where we saw how the cluster splits and can be represented in a tree. And so the lambda minimum is the minimum density needed to have a split into clusters, separate clusters. And of course, minimum density is the same as the inverse of the critical distance. So that's a notion of excess of mass. Then relative excess of mass, or also called persistence, is the persistence of a cluster is really the difference between when the cluster forms and when a point ceases to be part of the cluster. And so we have two notions. Lambda minimum, or the larger distance, is when the cluster forms. That's the first sea level. And then lambda p, for each point there's a separate one because some points stay in the cluster longer than other points. For lambda p, we have the associated density when that point splits off either to become a leaf by itself or to form a separate cluster. This is a discussion that I have for that in the workbook, and it's actually maybe easier to just read this. So this is our same example from before again. So we see at this level, the original single data set splits into two clusters. For this rightmost cluster, the excessive mass is the area under the curve. And that's it, because there's no further split. Here, there is a further split. So now the excessive mass is actually the persistence of the cluster is the difference between this intensity and the original intensity. So the original intensity is when this whole group splits off from the rest to form its own cluster. But then as the intensity goes up, there is a point here where it again splits into two leaf nodes. And so the difference between the maximum that in this case, there's only 2 points, the maximum that these points reach when they are still part of this cluster, and the initial minimum density value for the cluster to form, that is the relative excess of mass. And when we compute this for all the points in the cluster, because some points split off earlier than others, not in this example, but in the example that follows, you'll see that. So then we compute this for each point in the cluster, and that gives a sense of the stability of the cluster. And now, rather than using a uniform flat cutoff, we will look at the stability of the cluster and only keep those clusters that are the most stable. We will maximize the overall stability of the cluster. For example, here, this area, which is the persistence of, let's just call it cluster number 2, is much larger than the sum of the persistence of each of these little clusters. So using that criterion, we would not go to 3 clusters, but we would stay at 2, which is very different from what we would do with a uniform density cutoff. So that this notion of persistence and relative excessive mass is really what makes HDBSCAN different from DBSCAN and DBSCAN star. And this figure illustrates that, again, just what I just mentioned. So in this particular case, the sum of the areas, so at this level, the initial 2 cluster splits again and forms these blue and the yellow subclusters. In this case, the area of the blue and of the yellow together is larger than the area of the green. The red doesn't change. So we're trying to maximize the relative excess of mass. In this case, the maximum is reached by red, yellow, and blue. In this other case, the green area is much larger than the sum of the blue and the yellow. So if we try to maximize overall relative excessive mass, again, the red one doesn't change, but the green one is much larger than the sum of the yellow and the blue, so we stick with the green and with the red. That's the notion that hierarchical DBSCAN contributes. So let's look at how this works. Same general idea. We use the mutual reachability distance. We create a minimum spanning tree, but now we prune the tree. And we systematically go down in distance or up in density, depending on how you want to look at it, and start cutting the tree. And as we said before, in DBSCAN star, this results in a dendrogram tree structure. in DBSCAN SCAR, we have a flat cut. Here, we use this notion of relative excessive mass to create what we call a condensed dendrogram. And then in the condensed dendrogram, we will maximize the sum of the relative excessive mass of all the potential clusters that we could put together. Because in the end, just as you saw, everything becomes its own cluster. Every node is a leaf node, and we start where everything is one single cluster. So this is a splitting hierarchical clustering idea. So how does this work in practice? Here's our toy example again with the minimum spanning tree with the mutual reachability distance mentioned. This example is a little simplified on purpose to just illustrate the main concept. The details are in the lab notes, but basically it takes 2 points as the minimum distance, so then we don't have to worry about mutual reachability distance to change the locations of the points. But that's just to make it easier. What we're going to do is prune the tree. So first we take the largest mutual reachability distance and we cut 3 off. 3 becomes a leaf. Then everything else is one big cluster. And then we do the second cut. And here we have a bit of a problem because we have three edges that have the same length. So we can arbitrarily, at the end of the day, it doesn't matter where you cut, but you can do this 3 different ways and end up with the same result. So we cut here, and then we continue cutting. So now we have here initially our singleton, we have our singleton, and then this cluster of 6 points, and then this cluster of 2 points, and we keep cutting and cutting and cutting, and we can represent this as a tree structure. So this is the tree structure that corresponds to the pruning, cutting off branches of the initial minimum spanning tree. So there's all a tree analogy, cutting branches, pruning. So the first cut in blue is the associated density level. And as I've already mentioned a number of times, this is the inverse of the core distance. So as the density goes up, the distance gets tighter and we want closer and closer connected points. So the first cutoff is here. This is the first leaf node. And then because it's a leaf node, we start over here. This is the single cluster with everything. And at density 0.055, which is the inverse of 18, which was our second critical distance, we have a split into this cluster of 6 points and then this cluster of 2 points. And then for an even higher density at 0.067, this cluster of 2 points splits into leaf nodes. So let's now look at this notion of relative excessive mass. So we start with this cluster being split off into C3. C3 becomes a cluster for lambda minimum 0.055. Then 0.8 that is part of C3 splits off for lambda 0.067. So in the terminology of our expression, lambda min is 0.055, lambda p max is 0.067. So 0.012 is the contribution of 8 to the relative excessive mass. And then, of course, for 9, it's the same thing. So the whole relative excessive mass for cluster C3 is the sum of these two. And since the relative excessive mass of a leaf is 0, then it is maximized by keeping the 2 points together. And then we use the same logic here splitting off leaves, and as we go along, to figure out what is the relative excessive mass of the point, what is the point where we maximize the relative excessive mass in each of these clusters. And that is represented by this condensed dendrogram. So just to reiterate what I just said, we set the root to C1, we have the split in C2 and C3, and so when the split happens is 0.055, or the core is 18.3. When a point splits off, lambda is 0.067, or the core is 15, and the difference is the contribution. And so the total persistence of that cluster C3 is the sum over all the P. There's only two of them, so it's pretty simple. Then you can think of this as our example again with the splits of the, as the level increases, the clusters get split. They start as being 1 here, then they split into 2, and then the green one splits into 2 more. So we flip that around, and this is the so-called condensed dendrogram. And what we're going to do is apply a criterion. And we'll look at the parent. So this gray one is the parent in this class, in this case. And we compare the persistence of the parent to the persistence of the two children. And if the persistence of the parent is larger than that of the children, we stop. If the children are larger than the parent, we split. And this is what we carry out to obtain our condensed dendrogram. So rather than using one uniform cut, which is one distance or one density, if you wish, we use a relative notion where we measure the importance of the cluster by its persistence, by its relative excessive mass. And then we go down the tree, and if the parent has more persistence than the sum of the children, we stop. And the parent is the cluster that we retain. If, on the other hand, the sum of the children is larger than the parent, then we move one step further. And so we move through the dendrogram and compute this relative excessive mass at each split, and then decide which ones to keep. And the clusters that we keep, therefore, maximize the sum of the individual persistence. And for each cluster, the cutoff point, the core distance or the density, is different. So no more one size fits all. Each cluster is maximized based on how much of the density is among the points in that cluster. And so then a condensed tree plot looks like this. We'll see it in an actual example in a few minutes. So we start at the top. This is the point where we get a split into two clusters. So we compare the area in yellow to this area and this area, because this is the relative excessive mass from the point where the cluster forms, which is here, to the point where it splits, which is here. Oops, sorry. Right? So in this case, the sum of this area and this area is larger than the yellow area. And then here we're done. Here we have another split, and the sum of the two dark blue areas is larger than this lighter blue area. So we split, and these are the three resulting clusters. So as you can see, the core distance applied to get this cluster is different, is much larger than the core distance needed to get this second split of clusters. So that's the essence of HDBSCAN. Let me illustrate this. We again have our liquor stores, and just to refresh our memory, this is the uniform kernel, which, as we had seen previously, corresponds closely to the result found for DBSCAN. And HDBSCAN finds quite a different result because we have, first of all, we have only 5 clusters, and they are now include a whole cluster down here and out here in west, which we didn't have in the original DBSCAN results, which was very similar, which basically focused just on this region and ignored everything else. So by applying this notion of a relative excess of mass, the persistence of the cluster, and differential cutoff points, so differential critical distances, critical threshold from cluster to cluster, we get a different view of the densities in the data set. If we look at the condensed dendrogram, which is produced by GeoDa in this particular example, we see the same logic. We see how we look at the areas, and then different branches are selected as clusters. In this case, for example, this split is not carried out, and this is one of the clusters that we obtain. Here also this further split is not carried out. This is a leaf node. This split is not carried out. This remains the cluster, and so on. So you see the difference. Rather than cutting across uniformly as we did before, now we use these more subtle measures of the relative importance of the cluster. And you see, for example, this whole cluster is all the blue points, and some of these points stayed here, but others were split off to lower branches. So rather than having these all represented as separate clusters, they're grouped together because this relative excessive mass exceeds the sum of the branches, in this case of the children. So that's the essence of HDBSCAN. Is the same general idea as DBSCAN. We use distances, but rather than using the same distance for all as we did before, we now have this notion of a core distance, and each point has its own core distance, and associated with each core distance is a density which is the inverse of the core distance. So we replace the original points by a new layout based on the mutual reachability distance, which is the maximum of the core distances and the actual distance. Then we turn that into a minimum spanning tree, and we prune the tree. And after pruning the tree, we compute the persistence of each of the clusters, which is really the area under the part of the distribution that is associated with that cluster as long as it exists. And then we pick the clusters that have overall the largest stability, the largest persistence, the largest sum of the individual persistences. So it's a little bit different perspective from what we've seen before. Also note, no p-values. This is machine learning. This is not statistics, even though the origins of these density-based clustering methods came from statistics. So this is the end. This is the second module dealing with point patterns as such. In the next module, we'll move from the points to rates, which means that the points are aggregated to areal units and turned into proportions or rates. See you then.